So free chlorine is what we're going to use to measure today, but let's back up a little and just go into what chlorine is. So chlorine in water serves as a disinfectant, and if you own a pool, you probably know this and are familiar with this. It's also used in tap water to disinfect as well. I don't know why that gray box is there, but that's supposed to say chlorine in a standard form of gas exists as Cl2, and when it dissolves in water, it becomes two species or two forms. So collectively, those two forms of chlorine are known as free chlorine. So you have hypochlorous acid, the HClO, and you have the hypochlorite ion, which is ClO minus. So by itself, free chlorine has no color, which makes sense because if it had color, we'd see it in the pool and in our tap water. But when it reacts with a compound called DPD, which we'll use today, a magenta color is formed. And this intensity of the color is directly related to the concentration of free chlorine that's in the solution, and we're going to use that to our advantage today. If you have a pool and have used a pool testing kit before, you've used this principle just with different equipment, and you see the little color chart that you compare to. So we are kind of making our own color chart today, but we just have more precise equipment, that spectrophotometer, that's going to help us measure the concentrations using absorbance. And we're going to create some things and correlate that. So within the next slides, you'll kind of see more what the procedure is going to tell us. So another concept that's important to understand is what our equipment is actually doing today. So we have spectroscopy, which is the method for measuring light, and more specifically, spectrophotometry, which measures the amount of light that's passing through a solution. So we measure this by using a spectrophotometer, which in this case we're using Ocean Optics Red Tide, and this is the exact one pictured that we use in the lab today. And what that does is you see that little black square in the middle of it? On one end you have your light source, which is going to be set, for this machine, is set to 565 nanometers. You put a cuvette filled with your solution in the middle, and then you have your absorbance detector at the end. So what happens is that light source passes through the cuvette, and depending on the quality of the solution or the concentration of the solution in the cuvette, the light is broken apart, and only so much of it is going to be absorbed at the end, because some of the solution absorbs some of the light. So Beer-Lambert's law, through what he found, is going to tell us that the absorbance of light by a solution is directly related to its concentration. So essentially, the more light that's absorbed corresponds to a higher concentration. So essentially, the less light that makes it to that absorbance detector, the higher the concentration you have. And this can make sense if you think about all of the particles. If you have more of them in one solution, you're going to have less light that's able to shine through, kind of like a curtain. So once we make those measurements, we're going to form a calibration curve. And we do this so that we have an idea of the trend within our data, and then so that we can make some decisions and make some readings on some unknowns based on our measurements and the equipment we have. So we're going to make a calibration curve for this spectrophotometer using solutions of known concentrations. So you have two tables today. So this is table 1, and you have beaker 1 through 5. And that's going to have different concentrations. So you'll see us making these later, but notice that you add in that second column so much of the free chlorine standard, and then in the third column the amount of water. If you add those both together, the volume is going to be 25 milliliters total for each, but the ratio of free chlorine standard to DI water changes throughout each beaker. And that's going to result in different concentrations of those solutions. So beaker 1 is going to be a lower concentration, and then it's going to climb up from there, with beaker 5 being the highest concentration. So once we actually make our readings for our table 1, you guys are going to make the calibration curve. You can make it in Excel or by hand if it's neat, so you would need to use a ruler or something like that. We're going to use y equals mx plus b to figure it out, and make sure you get the right variables on the right axes before you graph. The best way to remember this, in general, when you're applying it, is your independent variable is x, so the x-axis, and your dependent variable is on the y-axis. And the best way you can kind of remember that also, if you can't decide which one goes on which one's independent, which one's not dependent, things like that, think about how you got it. So the concentration is the concentration, and that is independent of anything, but the absorbance reading is dependent upon the concentration. And spoiler alert, we are going to see that with higher concentrations, there's a linear and direct relationship with the absorbance. So as concentration increases, absorbance will increase too. Once we have all of the knowns, you have both x and y factors for them, so you can just plot the points, all 5 points, and then you can draw the best fit line. It's going to be one straight line. You're not connecting each dot to each other. You're going to draw one straight line that shows the best trend out of the data. And then we're going to do something a little bit different for the unknowns. So once you have the calibration curve graphed, you aren't graphing the unknowns on there. You don't put the points of the unknowns on that graph. They are separate. But we are going to use that calibration curve to figure out the identity of the unknowns. So what we can do is use the line equation from the calibration curve. We are going to determine the values for m and b. Remember that m is the slope of your equation, and b is the y-intercept, so where the line crosses y-intercept, or where x equals 0. What is the coordinate for y at that point? Then we have two variables left, right? When you're solving an equation, you want to be able to find one thing or have one unknown. So out between x and y, if y is absorbance units and x is the concentration in milligrams per liter, what will we already know about our unknowns? We are going to know absorbance because that's what we can read with the spectrophotometer. We don't know concentration, and that's what we're going to try to figure out, because if we know absorbance, we can plug this into our equation and solve for everything. So we're kind of like doing a reverse, and that's why you make the calibration curve first. Okay, last thing before you actually see video of the experiment, DPD is an irritant and it's hazard if it's ingested or inhaled. So breathing the fumes of the DPD is not good, and it's not good for women who are pregnant to handle this chemical because it can harm the fetus. So otherwise, all of the waste is going to go into a large beaker. We're going to just rinse that down the sink and let the water run, and then the clean cuvettes can be rinsed and just put in the used cuvette container. And we don't want to rinse them with alcohol, which you'll see. We're wearing gloves, goggles, and a lab coat as normal, and then you're going to see us dispose the waste, but you won't see us actually run the sink because you're not going to have to do that. So the first thing we have to do as far as getting our experiment started is let the electronics warm up, and then we'll go off and make our solutions. But first, we're going to plug everything in. So here we have a LabQuest 2 and a Red Tide USB 650 UV Ocean Optics. And essentially this is what's reading our absorbance. And this is kind of just like the computer screen that shows us and will tell us our readings. Otherwise, if we just had this, we wouldn't be able to get our measurements from the screen. So the first thing we have to do is plug everything in. There are two adapters here, so you just want to make sure you have the correct adapter with the correct equipment. Otherwise, you can risk frying the machines, and that's no fun and a kind of expensive mistake. And then the last thing you need is this tan cord here. That's going to help the two pieces of equipment talk to each other. And in a second, you'll hear the Red Tide reader hit on once this kind of wakes up, and there you go, you heard that click, and now you hear the fan running. So while this system is getting started, it takes usually a couple of seconds. We're going to switch the settings so that you can see me calibrate the machine at a better view. So now we've got everything set up and starting to run. This is usually the page you'll see, but if you ever get lost, you just want to hit the little app here that kind of looks like a speed dial, and that will take you to this screen. The first thing we need to do is correct the mode. Right now it's reading in full spectrum, but we want to go to this drop down menu here and do events with entry. We're not actually putting this onto a computer. Sometimes you can directly do that. So we're not going to specifically label anything. We're just taking the readings from this. So I'm going to hit OK. So now it should say events with entry, and it'll say event name, event. We don't really care about this here. The next thing is this red. This value is what you're actually going to see to record. These are our absorbance values. And it's reading 0 right now, which makes sense because there's nothing in this port here. But we need to correct what absorbance wavelength we're reading on. So right now it's at 0 nanometers. We're going to tap here, and we're going to change the wavelength to 565 as per the instructions. Hit OK. Then we're going to go ahead and calibrate the system. So it's going to do a 90-second warm-up here. We have already done the warm-up, but normally if you're starting this system for the first time, you would let this sit here. So I'm going to go ahead and skip the warm-up. Then it says place a blank cuvette in the device. And what it means by a blank cuvette is just a cuvette that has DI water and nothing else in it. So what I need to do first is take a Kim wipe and wipe the sides of our cuvette here and place it in this spot here. Now the beam that's running runs this way, so we need to make sure that the clear sides of the cuvette, as you can see this side is clear and this side is cloudy, we need to make sure the clear sides are being read, and the easiest way to figure that out is you can see this little triangle here. That indicates which side is the clear side. You generally want to carry cuvettes like this, and so you can clean them off with a Kim wipe like that. Once you've done so, you'll place that in there, and then we can hit finish calibration. It's taking a second to run, and then it will indicate that calibration is completed, and the sample time we're not too concerned about, so we hit OK. And now we're ready to go. This is a pretty good sign that our blank is sitting around 0 to 0.001 absorbance, because that means that there's nothing to reflect light off of in there, which is what we would expect. So we're gonna, now that this is all set up, we're gonna go make our solutions. Okay, so we're gonna go ahead and start by weighing out the DPD that we have. The DPD is essentially an indicator, because as you saw with the blank, the absorbance of the blank read about 0 absorbance units. And the reason that happened is because it was a clear colorless solution. So there was no colored light for the light of the machine to bounce off of. So what I'm going to show you right now is how the color changes when we add DPD. And so we're going to weigh out some DPD here. The instructions said to weigh out 0.005 grams of DPD, or 5 milligrams. And that's where you really want to pay attention to units, and also make sure you're writing units, because if you just put 0.005 and assumed people would know grams, that might not be the case. So I'm going to go ahead and tear here so the weigh boat is not red, especially important when we have such minute measurements. And we have this tiny little scupula to help us estimate the amount we need. And we're sitting at 0.3. 0.004 now. Sometimes it takes a little longer for this to adjust because it is such a small amount. So we have 0.005 grams, 0.06 now, and it's okay that I've overshot a little bit because I'm actually not going to put this one in the solution. I'm going to put this in our tap water here. So if you look at this solution, it is initially a clear and colorless solution. And what it truly is just the tap water in from our sink here. This is not DI water, this is regular tap water. And so I'm going to go ahead and add the DPD to it. And the way I'm going to do that is take from the solution and then rinse the DPD down. We want to make sure we get all of it in there. And this is not necessarily part of the experiment, but I wanted to show you, A, to demonstrate how DPD works and what it's for, and B, so you can see a little real-world experience, because this is showing us that we have chlorine in our tap water here. And it has gone from a colorless clear solution to a clear solution with some amount of color. So after you do your lab, based on the color, you might be able to estimate how much chlorine we have in the tap water here. So the next thing, are you still recording? So the next thing we're gonna go ahead and do is actually mix together our solutions here. So for the 0.40 ppm solution, I need 1 milliliter of the 10 ppm stock solution and 24 milliliters of regular DI water. So I'm gonna go ahead and pour the 1 milliliter first. I'm gonna use a disposable pipette because it's such a small amount, I don't wanna over pour here. So I'm gonna bend at the waist to make sure I've lined up the lines of the graduated cylinder here. And I don't wanna bend at the knees, because if this chemical does spill into my face, bending at the hip allows me to have a better reaction time than bending at the knees would, and it reduces the danger here. So I've got a very accurate 1 milliliter here. And now I'm gonna go ahead and pour my 24 milliliters. This is a 25 milliliter graduated cylinder, so I'm gonna be wanting to shoot for right here. And to get the efficiency in a pour, I have used my non-analytical glassware to estimate about, and I really underestimated. I put a little bit under the 25 milliliter mark here, and I'm gonna pour into my analytical glassware so I can know that I have exactly what I want. So I'm gonna stop before I hit the line because I don't wanna over pour, and then I'm gonna grab a disposable pipette again so I can get closer to the mark. And same thing, I'm gonna bend at the hip. Make sure that line is 1 and lined up, and fill my meniscus to that line. So we've done that in all of these cases here. We've pre-poured everything else. So the last thing I'm going to do is mix our stock solution with our DI water and add the DPD. So this is going to make our smallest solution here. This is the 0.40 ppm. Going to add our water. So we're making 25 milliliters of each solution, and our last little thing is we're going to mix in the DPD. And you can potentially see it's already changed color, so as we go, you might see a trend in the color. Water. And we're using a different pipette each time because we do not want to cross-contaminate between samples here. And this is why we're using disposable pipettes too. It just makes it a little bit easier. And I'm just going to carefully make sure that all of the DPD makes it in there. See now, for our 1.20 ppm, we have a little bit more. We have 3 milliliters of our stock solution. And it makes sense that the higher concentration solutions would have more of the stock solution each time. And basically what happens is the more stock solution we have, the less water we put in to keep it at 25 milliliters each. Now to our 2 ppm, we're using 5 milliliters of the stock solution, and this can all be found in the chart in your PowerPoint slides or in your document background, experiment background. The last one we're going to go ahead to do is the 4 ppm solution. So we are using 10 milliliters of our stock solution and 15 milliliters of water. Add that DPD. I got a little bit of a spill there, but that's good because I actually did want to talk to you about spills in science. Luckily this spilled on the paper towel, but if it had gotten on the counter, we would want to make sure that we did our job wiping it up. In this case, this is just water and chlorine stock solution, which is safe for us to pour down the sink and wipe up, but if it were an acid or a base, we would need to talk to our instructor and clean it up accordingly. The last thing you want to do is make sure that you are responsible for cleaning up all your spills, because if you see a puddle of some solution in the lab, if it's a clear colorless liquid like this one is, I don't know if that's water, I don't know if that's acid, so if I go to wipe it up with a paper towel, and especially if I don't have gloves on, I could get hurt. This is a little bit smaller, but you still want to make sure you're cleaning up your messes so that someone else doesn't have to be faced with the confusion of spilling something or cleaning up something unknown to them. So we'll go ahead and give you a nice gradient of our stock solutions here. And as you can see, the higher the concentration, the darker pink we get. Next, we're going to move on to our unknown solutions. Okay, so you can see here, these are our 5 known solutions that we just made, and then we have our 5 unknowns here. So in total, we have 10 solutions. We have 11 cuvettes, and the reason we have 1 extra is because we need to have that blank solution. So we're going to fill that with deionized water, and I'm going to show a clip to you real quick explaining the importance of picking your cuvettes accordingly. And I'm going to show you the difference between different styles of cuvettes. So as far as the styles of cuvette go, you can just see that these are a little bit different than the ones that you'll see me putting into the spectrophotometer later in the video. They're basically the same thing, except the optical window on these is smaller. And in this image, you can see the optical window is circled in all those 3 spaces. That is where the light is going to actually pass through. These are a little bit like fancier, and the optical window is minimized, but in the ones we're using in the actual experiment, those have more of an open face, and they're clear on 2 sides and then cloudy on 2 other sides, and basically you know which way to have them facing because of the triangle on the one side, and that's going to tell you which way it should be facing, and that's going to be better explained in another clip where I'm putting the cuvettes in the spectrophotometer. More importantly, what I wanted to talk about on the slide were how you choose cuvettes and just making sure that you inspect them as you should with any of your pieces of equipment in a lab. So cuvettes, again, we're looking at light passing through them, so any blemish or scratch on them is going to affect the light passing through. So if it's scratched or has fingerprints on it, we need to make sure the fingerprints are cleaned off, and we need to make sure to avoid using scratched ones. So you can see on the left here that those cuvettes have a good amount of damage in the optical window. If they're scratched above there, or if they're Sharpie above it, that's not going to matter because that's not where the actual light is passing through. So you want to make sure you're looking at a detailed search as to where the scratches are and if they're happening, and basically discard them or just put them in a pile so they don't get used. On the right is a pretty good example. There is some dust on it, but that can get cleaned off. That's a good example of a nice clean cuvette. So now we can go back to looking at our actual solutions.
Alright, so now that you've seen the process of picking cuvettes, which is what you would do in the lab, you're going to grab one of these trays and label it. In this case, the people who labeled it did unknown on the top and then known on the bottom here, and they labeled 1 through 5 blank and then 1 through 5. So I'm going to follow what they did. Sometimes you get lucky with a blank slate, or you can follow someone else's. It's not too crazy either way. They say to add about 2 milliliters of the solution in here, but what my goal is to just essentially fill around this line. What you want to do, and sometimes if everyone fills to this line, it'll make us run out of solution in lab, because these are technically in a normal lab communal. So as long as you get above the mark on the Ocean Tide reader, it's okay. But in this case, I'm just going to fill them up to the max since we're not sharing solutions today. So I'll start with the unknowns, unknown 1. And what's nice about the cuvettes too is it helps you compare and make observations about the different colors you see. And so this is a really important time to make sure you know the difference between colorless and clear. And if you have proper observations about the solutions, it might help your discussion later be a little bit more thorough. And it may help you explain different trends that you see. We generally don't want to write on the cuvettes because like you saw with the different scratches, it gets in the way of the reading and it just makes it harder for reuse, because we do clean these out. Next, I'm going to fill a blank. This is also the blank you would have used to calibrate your machine. And then we're going to move on to our knowns. So we're going to go 1 through 5 here. I'm pretty sure that's the table's order of it as well, is lowest to highest. And here's our last one. So we're going to go ahead and take a picture of this and show you at a little bit better angle so it's not as cloudy on the video. But this is generally your trend. So in the front you see your known solutions here, going from least concentrated to the highest concentration. And this is nice compare to the blank here. And then if we turn around, we've got our unknowns here. So unknown 1, 2, 3, 4, and 5. And I'll give you a little bit of a background to help you distinguish between them. So next we'll go over and we'll take these over to the Red Tide optics and we'll show you how to actually process them.
Okay, I lied slightly. I wanted to show you the visual results before we actually started running this through the spectrophotometer. So just take a minute, pause the video, and record some observations about the colors that you see, you know, the gradation that you see and how that changes based on what you know about the knowns, and make some predictions about the unknowns based on their colors and different things like that. One thing I want to note while we are here and making observations, because we haven't really gotten a chance to talk about it yet, when we're talking about solutions, something can be clear and have a color. So clear refers to the quality of the solution. So if it's very cloudy or if you can see completely through it. Whereas if it has no color, which a lot of people say is the same thing as clear, we actually want to say it is colorless, or it has color. So for instance, the blank is colorless and clear, whereas unknown 5 has a darkish pink solution that is also clear. So just a little difference, but go ahead, pause the video and make your observations now before we actually start running. And when we run the data through that spec, make sure, don't worry about writing anything down. We're going to have the raw data on Blackboard for you.
Okay, so now we're back to our setup here. You can see this is reading negative because there's nothing filling this port right here. I've got some white paper to kind of show you everything in between. Off the screen, I've got some Kim wipes that I'm going to be using. These are really helpful to clean the cuvettes. You can clean your glasses with them, any glassware that needs, like, clarifying. They're really, really nice. But generally, we're only going to use one of them per cuvette, so we're getting new ones each time off screen, and then we've got the tray of our samples here off screen as well. So the number that we're going to be focused on recording, like I said earlier, is right here, and I'm going to do a blank correction in between each sample. So this is our blank, and we're just going to start to make sure we're still sitting at a good spot, and I need to clean with the cuvette. And it's going to bounce back and forth a little bit, but we're going to let it stabilize. Okay, so it's sat on 0 predominantly. So we're going to keep it there. And I don't actually have to hit anything recorded here. The first one I'm going to start with is known 1. So here's, just so you can kind of get an idea of the color. Known 2, and I'm going to go in order from here. And you'll be able to find the raw data on Blackboard for you to check. And you'll see me blank correcting in between each one. And if you forget to do it, that's okay. You can just blank correct. And put your sample in again. Okay, and that just helps the machine get back everything. So from here, this is a pretty repetitive movement, so I'm going to speed up the process and just kind of make it go a little bit faster for all of you. So now I'm going to switch to the unknowns here. So we've got unknown 1, Okay, so for our cleanup today, it's relatively simple. All pipettes can go in the trash. They don't have to go in the solid hazardous waste because we don't have hazardous waste today. Our solutions, like you saw, it's just chlorine. There's already chlorine in the water supply, so we can dump these down the sink, no problem. We're gonna go ahead and rinse with DI water. 2 or 3 times is usually a good estimate to get everything out. And the last thing is this glassware is not completely dry. If you saw, we did the right thing, which was labeling the glassware, and now there's Sharpie on that. This will not always be filled with 4.0 ppm solution, so what we need to do is wipe that off as well. It's just common courtesy. So what we do, Sharpie is usually pretty permanent, but something that does wipe it away is alcohol-based things. So today we're going to use ethyl alcohol. You can also use isopropyl alcohol or acetone. I'm going to squirt a little on a Kim wipe here. Don't need too much, and wipes away like it was never there. Then we're going to just rinse it with our DI water one more time. We can dry off the outside and then put it back on our glassware rack to dry off later. With our cuvettes though, like we saw, sometimes they had Sharpie on them, and that's from past labs, but we do not want to clean these out with our alcohol because this is plastic, and the alcohol-based solutions are going to craze or crack and essentially ruin the cuvettes. So to dry out these insides, we can use a Kim wipe and kind of just like poke it down there with a pipette, or we can use the air blast from that little air thing that we've seen, which you'll learn when you finally get into a physical lab too. So that is essentially how we clean everything up today.
Okay, so now we're going to start the graphing portion. If you want to make your graph in Excel, like I said, you totally can. Just make sure you either have it calculate the line equation for you, or that you do that by hand, which I'll show you after I graph this. To start with some materials, I've got my lab notebook. Graphing paper is really helpful for this, but not needed. I've got my pen. Again, we want things done in pen, and some instructors are picky about color. I personally don't care about it. Excuse me, sorry. So then the last thing I've got is a ruler because we want our work to be nice and neat. This is just, it straightens out to be a little bit longer, but that is our ruler there. So I'm going to be doing a very general overview here, but this is just kind of the basics for graphing, and you're going to have to graph in future labs, so this will help you too. So we're going to start just with the general axes of our lab. We've all graphed before, so I'm just going to go ahead and start. It doesn't have to be too big because there's not too much range. So we've got our y-axis and our x. And if you want, you remember to leave just space over here and space down here. You can always do your data table. Well, your data table is going to be bigger, so never mind. But you can do data table and then graph, or do it on as many pages as you needed. Just don't make it cramped. That's the big thing. So the next thing we need to do is we want to leave room for the actual graduation tick marks. So you would go through and, you know, see how much space you need, and then, you know, draw those in and put your actual numbers, things like that, and so on. And I'm going to label this, we can label this Y if we want, and then I'm going to label the axis, which is important. So this is our dependent variable, absorbance, and I'm going to put the units. So this is in absorbance units, which is abbreviated with AU. Then on the bottom we'll save room for numbers as well, and this is going to be the concentration of free chlorine. You can write free chlorine concentration. I'm just going to put these marks around it because that is another way to signify that it's the concentration of something. And then we're going to measure this in ppm or milligrams per liter, whichever you prefer to put. Just make sure you're consistent. So So then you want to make sure you plot all 5 of your points. So I'm going to just plot some randomly. That one's pretty nice, but I'm going to add one just for teaching purposes, a little outside of the trend. And then make sure you put where your blank lies. So in this experiment, our blank was at 0, which was nice. Sometimes it's a little bit higher than 0. So now we're going to do our line of best fit. I am not going to draw a line in between all of these. We're not doing that. So what we're going to do is we're going to get our ruler, and generally you want to find the line that best represents kind of the mean of these values. So if I did the 2 endpoints, I don't think that's a great representation of all of these points. So I'm actually going to move this in a little bit, keeping base on this endpoint here in the blank, just move it in slightly so we can get a pretty good representation. If you want to do this with pencil a few times to practice, because it's kind of hard unless you have a clear ruler to know. And then we're just going to go ahead and draw that line. So I would say that's a pretty good representation. Some might agree, some might not. This is why we have computers actually do these for us in the lifetime. So this is where we're done with the known values. We've plotted them and everything. So the next step is to calculate our line equation. So remember that the line equation is y equals mx plus b. So before we can actually make our line equation, we need to solve for some factors separately. So y and x stay in the equation as general things. The y represents the absorbance, x represents free chlorine. M represents the slope, and b represents the y-intercept, which is where the line crosses the y-axis. So we're going to start with the y-intercept because it's a little, actually no, we can't start with the y-intercept, sorry. We're going to start with the m because we need m to solve for b later, which you'll see. So m has its own equation, and that's a slope equation. You remember that m, or slope, is rise over run, and the mathematical way to display that is the change in 2 points in the y direction, so y2 minus y1, divided by the change in 2 points in the x direction. So we are going to take, generally you want to do 2 points that are close to the line, and they're kind of far apart. So you could pick, you know, maybe these two, or this one I would say is close enough, so you could do this one and this one, and you're going to plug those values in. So we would plug the absorbance value for this one here minus the absorbance value for this point here, divided by the concentration minus the concentration. And then you're going to make sure you keep your sig figs in mind. They're important. So that will be your M, and then you can plug that in. And then you're going to have your B that you can solve for. So now we're going to hop over, and B is our y-intercept. So let's solve and manipulate this equation into a solution for B. So we're going to say y equals mx plus b. So we can subtract b, and we can say, or sorry, subtract mx, so we can say y minus mx is equal to b. Sorry, I just wanted to make sure that was clear for you all. So now what we can do is, knowing that this is when the line is crossed, we're going to plug in, because saying it crosses the y-intercept is also saying what is the value of y at when x is 0. So we can plug in the x value, the slope value, but it's just going to equal 0 anyway in this case. So in this case, whatever our blank was is equal to b. So in this case, that was 0.000 AU is equal to b. What I didn't quite say correctly here is that I wanted to say you can't always, you don't always have an actual x value that crosses at 0. So your y-intercept isn't always going to have that. And so what you can do is pick 2 other points and solve for what b would be also. I didn't do the best job of explaining that, so that's why I wanted to do that voiceover really quickly. I apologize, but there are plenty of videos out on the internet if this is confusing about how to find the y-intercept. So you can reach out for those or just reach out to your instructor and we can explain it better than I did here, so I apologize. Went on a tangent with that, so we're just gonna go back. Now we have our line equation. So you're gonna write this out and report it in your discussion. So you're gonna state that y equals whatever value m was, x. Technically it's plus that 0.0. For this case, we'll just say this is like 0.01. But since it's equal to 0, it's kind of useless. So we can say our line equation is 0.01 x. Now, what we do with this is we're going to find our unknown. So what's cool about our unknowns is we know one of the values in this equation. We recorded the absorbance, right? So we know y, and we want to solve for x. So let's change this to solve for x. So in order to do that, we're going to divide by our slope. So we're going to get x is equal to y divided by 0.01. And you can have the units however you need. Then you're going to plug in the y value, or the absorbance value, of your table or of your unknown, and it's going to report that concentration, and you're going to fill in your table too. So that's essentially your calculation sections. Then once you have this, you're going to get some answer x, right? And then on some slide, or in the raw data, we are going to tell you what the identities of the unknowns are, and then you need to compare those to the actual values, or the theoretical values, and compute your percent error, which you should know by now how to do that. If you have any questions, just reach out to your instructor.